Welcome to our introductory lecture on R programming for core empirical research methods at the University of Oxford. This lecture is going to be a lightning introduction to base R programming. Base R means R without any bells or whistles, no packages, and you're going to have to start by doing things the hard way. The analogy here is that we have calculators, but kids still need to learn addition. So just like we have amazing packages such as dplyr and ggplot, which we're going to learn about in future lectures, you still got to start off by learning some base R. This lecture is going to move pretty fast because I already assume that most of you have at least some programming knowledge. So in particular, I'm going to assume that you understand things like variables, if then, for while, and so on, at least to some basic level. I will not assume any prior knowledge of exposure to R, however. So that means that I'm going to be moving pretty quickly, but I will focus on how things work in R. If your programming background is a bit weak or rusty, you can definitely still catch up, nothing to fear, but you just need to make sure that you put in the hours from the start of the course. Needless to say, one lecture is not going to be able to cover everything there is to know about base R. The point of this lecture is to serve as a starting point to help you learn more. So you're going to be developing skills and confidence that you can use to teach yourself more things. These skills involve experimentation, trying things out and seeing what happens, and starting to learn how to get help from the R help files, from internet resources, from your fellow classmates, and indeed even from large language models, and we'll have more to say about that in class. There are some suggested readings. If you click on these links, you'll be taken to them. I have a book for you called Hands-on Programming with R, and I also have my notes for that book. There's also a fantastic book called Advanced R that goes somewhat beyond what we're going to be covering in this course, but if you already have significant programming experience in another language and you'd like to have a deeper understanding for how R works, this is a great resource. Let's get started with some basics. Good programming style is crucial. It's one of the things I'm going to emphasize in this course, and it's a skill that you're going to have to develop. When I program in R, I follow the Tidyverse style guide. If you click on this link, you can see what that style guide entails. You should follow this style guide too. This is actually one of the marking criteria for the course, and I'm not just doing that to be difficult. I'm doing it because it's really valuable to learn how to write code that's easy for others to understand, and a great way to do that is by using a consistent style. Don't fret. All you've got to do is follow my lead when it comes to spacing, indentation, and so on. You'll get the hang of it in no time. Naming objects is important, and it's also hard. So let's start off by talking about a couple of rules. First of all, names in R can only contain letters, digits, the dot, and the underscore. They can only start with either a letter or the dot. You shouldn't use a name that's already an R command. While R will let you do that, it can cause all kinds of confusion. For example, you could technically redefine false to be true, but all that's going to do is confuse people. So please stay away from that if you can. If you click on this link, you can see some more about naming things from the Tidyverse style guide. Some key suggestions here are to only use lowercase letters, numbers, and the underscore. I should say it's not a suggestion. That's actually part of the Tidyverse style guide. To use what's called snake case, that's where you separate words using underscores, and to choose names that are concise and also meaningful. Any line of R code that begins with this hashtag is a comment. I'm never sure if it's a hashtag or a sharp sign from music, but one or the other. Comments are not for the computer, they're for humans. They're things that we insert into the code to try to make it easy for others to understand. Again, drawing from the Tidyverse style guide, comments should always begin with this hashtag and then be followed by a space before you start actually typing out the comment itself. You should capitalize, and you should put a period at the end if there's at least 2 sentences. As a general guideline, comments should explain the why rather than the what or the how of code. If you're writing clean code, the what and the how should actually be fairly apparent. If you find yourself writing too many comments, it's possible that what's really going on is that you've written unclear code. So you may want to actually start again. Now, perhaps the most important thing to know in base R, the R assignment operator. It's a less than sign followed by a hyphen. So x, and then this less than hyphen 3, creates an object named x with the value of 3. You can either enter this assignment operator by typing it out explicitly, or inside of RStudio, you can type Alt- on your keyboard, which will insert it automatically. There's actually a little bit of subtlety around what it means to assign a value to an object. And if you want to learn more, although it's not really necessary for this course, you can take a look at this chapter in Advanced R, which I've linked from the slides. If you want to read out this assignment operation, you don't actually say x less than hyphen 3. Instead, we have a convention that we use to denote assignment, and that convention is gets. So to read the assignment operation on this slide, we would say x gets 3. A single equal sign can also be used for assignment in R, but it's considered bad style, so please avoid it. Here are a couple of simple examples. The first one is taken directly from the previous slide. The next one is bad style, but it also works. Don't do it, but I just want to show you what it does. The third one, which has the assignment operator running in the wrong direction, so with the arrow pointing to the right, also works. But this is considered super bad style, so please don't do it. One of the first things you can do with R is you can use it as an overgrown calculator. You can carry out basic arithmetic with plus, minus, asterisk for multiply, and a slash for divide, and you can group terms together using parentheses. One really important thing to bear in mind, and a common mistake that people make when they're just getting started with R, is to try to use implied multiplication. So for example, trying to write 2x just by writing the number 2 next to the character x, that doesn't work. So in R, you have to use the asterisk to denote multiplication. And here you can see an example of the sort of error message that you'll get if you forget and you try to use implied multiplication. Don't feel bad if you do this from time to time. I've been using R for nearly 20 years, and every now and again, I still do it myself. In addition to the basic arithmetic operations, R also has exponentiation. So to raise a number to a power, we use this caret. So 2 caret 8 gives us 2 to the 8, which is 256. And if you want to access e, so the base of the natural logarithm, to calculate e to some power, you use the command exp. So exp of 1 is 2.718282, and so on. R also has a built-in logarithm function. It is called log, helpfully. It defaults to the natural log, but if you want to specify a base other than e, you can do so. You just have to supply this additional function argument, base equals b. So here's an example. To take the log base 10 of 100, we type log 100, comma, base equals 10. And as expected, that gives us 2. Whereas if we don't supply the base equals 10, we're getting the natural log of 100, which is about 4.6. R has a number of data types. These are going to become increasingly important as we move on. So let's get started by going through the basic types that we'll need. The first group of types is called numeric types. Double is the default numeric type. So when we created this variable x, when we assigned it the value 3, that was in fact a double. R also has an explicit integer type. You can create this by using the capital letter L. So if we wrote x gets 3L, that would create a variable x that takes on the value 3, but 3 is stored not as a double, but as an integer. If you're thinking to yourself, what on earth is he talking about? What's the difference between a double and an integer? You might want to take a look at this blog post that I wrote that talks about floating point arithmetic. It's not absolutely crucial for the course, but if you're curious, you might want to take a look. If you've already programmed before, I imagine you have some idea what I'm talking about when I distinguish between different types. The next type we need to think about is character type. This is a chunk of text stored within single or double quotes. So here we have X gets hello world or Y gets ERM rocks. Either single or double quotes work, although there are some situations in which you can get into trouble with single quotes that you'll see in some examples later on. The third key type that we need to think about is called the logical type. In some other languages, this is called Boolean, and this just means true or false. To find the type of something in R, there's a handy function called type of. Let's play around with this. So X gets 3.14159. If I do type of X, I will see double, because this is a numeric type, and in particular, it's a double type. Remember, that's R's default type. In the next example, I've got Y gets 10L and Z gets 10. If I run type of Y, I'll get integer, whereas if I run type of Z, I'll get double. Economist underscore buried nearby gets Francis Isidro Edgeworth. And there, I'm assuming you're inside the Manor Road building, because if you are, there really is a famous economist buried nearby. If we run type of economist buried nearby, we will see character, because this is a character type. Finally, type of true returns logical, because true is a logical type. Logical operators are pretty important because we use them for doing logic, and logic is central to everything that's happening on a computer at some fundamental level. So R has logical operators for all the basic operations you might be familiar with. Not. So not turns a true into a false and vice versa. And in R, we use an exclamation point to denote not. Sometimes that's called a bang. And is a logical operator that returns true if both X and Y are true. X and Y, again, is true if and only if both X and Y are true. In R, the logical operator for and is an ampersand. Or is a logical operator that returns true if and only if at least one of the two conditions is true. In R, the logical operator for or is this vertical bar. Finally, we have the dreaded XOR. XOR is actually different from OR. XOR stands for exclusive OR, and exclusive OR is true if and only if exactly one of the conditions is true. To obtain the exclusive OR in R, we use this function XOR, and it takes two input arguments, X, Y. So to explain the distinction between OR and XOR, here's a little example that I was taught when I took my first programming course. If your mother says you can go to the dinner, if your mother says you can go to the movies if you do the dishes or you clean your room, suppose that you both do the dishes and clean your room. Then you still get to go to the movies because your mom is actually using the usual garden variety or in that statement. If your mom was extremely weird or perhaps a logician, she might have said, you can go to the movies if you do the dishes XOR clean your room. In that case, if you were to both clean your room and do the dishes, your very unusual mother would actually forbid you from going to the movies. So that's the distinction between OR and XOR. Here's a few examples with these logical operators. Nothing too exciting. Not true, unsurprisingly, returns false. True and false returns false. True and true returns true. True or false returns true. True or true returns true. XOR true, false returns true. And here it is, XOR true, true returns false. The next set of operators we need to understand in R, after logical operators, are called relational operators. These operators also return true or false, and they're used to compare things. So less than, greater than, less than or equal to, and greater than or equal to all mean exactly what you think they do. They mean what they mean in mathematics. Double equals, on the other hand, is a test for equality. So double equals is going to return true if the thing on the left and on the right of the double equals are equal. A really common mistake that everybody makes from time to time, especially when you're starting out in programming, is to confuse double equals with single equals. They are very different. Double equals is a test for equality. Single equals is an assignment operator or a way of supplying an argument to a function. Not equals, which is just an exclamation point followed by equals, on the other hand, tests for a lack of equality. So this is basically the opposite of double equals. Here's a few examples. 5 greater than 3 returns true because that's a true statement. 2 less than 2 returns false because that's a false statement. But 7 less than or equal to 7 returns true, as does 9 greater than or equal to 9 because those are both true statements. Similarly, -1 double equals -1 returns true because those two things are equal. But 5 double equals 2 returns false. 0 not equal to 0 returns false because that's the opposite of double equals. 0 equals 0, and so it's not true that 0 doesn't equal 0. And I'm realizing now that was needlessly confusing, but, well, it's just an example. 75 not equal to 42, on the other hand, returns true because 75 and 42 are not equal to each other. Now, I've just taught you double equals and not equals, and I need to immediately warn you that these are actually pretty dangerous. So in general, although there are some minor exceptions, in general, you really don't want to be using these very often in R. So in particular, if you need to make sure that you're returning a single true or false value, you should be using the function identical. Another thing to be aware of is testing the equality of doubles can give weirdly unexpected results. A few slides back, I mentioned a post on my blog, and it talks about one situation in which that occurs. The way around this latter issue, which stems from the fact that computers can't actually represent real numbers perfectly, and they can only approximate them, is to use a function called all.equal. This tests for what is called near equality. So typically on a computer, if you're trying to see if two double values are the same, you don't actually want to be using identical. You want to be using all.equal. NAs, infs, and NANs. What on earth are these? Well, these are some very special keywords in R that refer to important objects that we sometimes need to compute with. None of these things is actually a number, but all of them can be the result of a calculation with numerical values, depending on what that calculation was. And you can actually do math with all of these special values. In R, NA means not available, or in other words, missing. If some kind of value is NA, that means we don't have access to it. We don't know what it is. Inf, on the other hand, means infinity, and minus inf means minus infinity. NaN, on the other hand, means not a number. You may be wondering what's the difference between NaN and inf. Well, NaN is basically what you see whenever there's a calculation that is undefined. So something like 0 over 0, whereas inf and minus inf are what you would encounter when there's a value that is in fact infinite. And again, you can do math with all of these in R. So let's take a look here. NA plus 1 returns NA. And what on earth does that mean? Well, NA, whenever you encounter that, you should just read it as, I don't know what the value of this number is. So NA plus 1 means I added 1 to some number, and I don't know what the value of that number is. What's the only possible result? Well, it's NA. Because if you don't know what the first number is and you add 1 to it, then you definitely don't know what the answer is. 2 times inf, on the other hand, is inf. And that's because any constant times infinity, any finite constant, is definitely infinity. So let's take a look at another way to get infinity. -1 over 0 Basically, what R is doing here is it's interpreting this like a limit. So -1/0 isn't well defined, but you can imagine taking -1 and dividing it by smaller and smaller and smaller values. If you did that, the result would tend to -infinity. Similarly, if you take 1 and divide it by inf, R is interpreting that to mean taking 1 and dividing it by successively larger and larger numbers, taking a limit, the result would be 0. 0 divided by 0, on the other hand, is undefined. If you want to think about that from the perspective of limits, you can think about it as follows. If I tell you that the numerator and denominator of a fraction both tend to 0, that's not actually enough information to see where the whole fraction tends. You'd have to know the rates at which each of those things approaches 0. And since you can't tell what the answer is, but it's not really missing, it's not that we don't know one of the key inputs. We have an NaN rather than an Na. Let me repeat that last thing one time. In the calculation 0/0, the problem isn't that we don't know one of the inputs to the calculation. We know perfectly well that we're taking 0 and dividing by 0. The problem is that that particular quotient is not well defined. So there are various ways to test the type of an object in R. I already showed you type of, but there are some other ways that involve testing for a specific type and return a logical value, a true or false. They are displayed on the following slide. Is.integer is a way to test if something is an integer, and you can see here 2 examples of that in action. Remember, 3L is an integer, but 3 isn't. Is.na is used to test if something is a missing value. 4 is not a missing value, so we have a return value of false, whereas na is indeed a missing value, so this function returns true. Is_character tests for character types. And as you can see here, is_character of na returns false, whereas is_character of hi mom returns true. And finally, we have is_double, and in this case, remember 3 is a double, but 3L isn't. And that brings us to the end of part 1 of this video. So at this stage, you should pause, ponder, review the material if you need to, and then attempt the following exercises. All of the solutions to this exercise and the others in all of the slides for this course are available on the course website. So after you've attempted these on your own, I'd encourage you to head over to the website and check your work.